A caracal with mass 11.8 kilograms can jump as high as 3 meters to try to catch a bird. Suppose that the caracal has 0.50 seconds of acceleration before it leaves the ground. What is the average force acting on the caracal by the ground? So right here we have some equations. The first one is the impulse momentum theorem, which states that a force times a given time interval is equal to the change in momentum of that object. And momentum is just the mass times the velocity. And then we have this kinematic equation, which says that the final velocity squared is equal to the initial velocity squared plus 2a times the displacement. So, and here is a free body diagram. This one shows the normal force and the force of gravity. Those are the only two forces acting on the caracal during its jump. So to find out the change in momentum, we first need to find out its velocity, since the momentum is mass times velocity. And we do not know the velocity as it leaves the ground. So we first need to figure out the velocity just as it leaves the ground. And that's where this equation comes in. So we can rearrange this to solve for the initial velocity. And the final velocity is going to be 0, since once it displaces 3 meters, it's at the top of its jump. So its vertical velocity is 0. It's at the top of its jump. And then it's going to reverse direction and come down. So the final velocity, we can set that to 0. And then if you solve that equation, 0 equals the initial velocity squared plus 2a times the displacement. For the initial velocity, you get that the initial velocity is equal to the square root of minus 2a times the displacement. And once again, you can ignore final velocity. The final velocity is 0 after it displaces 3 meters. Now you can plug all of your variables in, but we don't need to do that just yet. Now we can figure out the second part by figuring out the average force. So we're going to use this equation right here. The force times the time interval is equal to the change in momentum. So the force is simply the normal force minus the force of gravity. You can see that in the free body diagram right here. So the normal force minus the force of gravity times the time interval is equal to the change in momentum. So that's going to be like the momentum, the final momentum minus the initial momentum. And the initial momentum is 0, since it has no velocity when it's on the ground. It's just starting, it starts from rest. So we can just ignore that since it has no initial momentum. So then we have that the normal force minus the force of gravity times the time interval is just equal to its momentum at that instant when it leaves the ground. So we need to solve this for the normal force, since that is what is acting on it. That's the force that it exerts on the ground. The normal force, if you solve this, is equal to the force of gravity plus the momentum over the time interval. And then now we can just simply substitute our equation for velocity into there. So then we get that the normal force is equal to the force of gravity plus the mass times the velocity at that instant, just the square root of minus 2a times the displacement. And we're going to divide that by the time interval. Now that we have this equation, we can solve this by plugging in all of our variables. Make a little bit more space. Get rid of this right here. And now we can just plug everything back in. So the normal force is equal to the mass of 11.8 kilograms times the acceleration due to gravity of 9.8 plus 11.8. Again, that's the mass. Then times the square root of minus 2 times the acceleration of minus 9.8. Again, these two negatives cancel, so you will have a square root. And then times the displacement of 3 meters into the air. And then on the bottom, we need to insert a time interval of half a second. So now if you solve this, you should get that normal force is equal to 297 newtons.